The stem and leaf plots, the histograms, and the summary measures all give one little piece of the puzzle about trying to describe data. Box plots are another way to do so and begin to craft the identity of the data, and they help to kind of combine a couple of features all together. And you see this list here on already laid out. The measure of center, spread, asymmetry, and identification of outliers or unusual observations can be aided by the box plot. They tend to show up more when people are looking at quality control, particularly as they compare, say, one plant to another type of plant. Now let's just look at, for our cyclic testing of our aluminum test coupons, what this data might look like as we create this box plot. And the big thing here that we're going to be doing is creating the quartiles. Remember that, say we want the lower quartile, that's the lower 25%. So the probability, in a sense, that our observations are less than this quartile is 25%. And that's just a matter of going into your data, ordering them from high to low, and coming up with then that 25th percentile, which for our data that we have for the aluminum tests is 1102. Okay, so we're going to come in here at 1102, and I'm going to craft this, of course, just by hand. There are certainly many statistical packages that will enable you to do this very quickly. Excel is not one of them. To do this in Excel is actually quite a lot of work. The second quartile is the same as the median, and so now you're talking about the 50th percentile for this particular data. That is 1436.5. So again, to a rough kind of scale, that's about here. And so that's about 300 apart from that one. And then our third quartile, you may have guessed, is going to be associated with that 75th percentile, and in this particular case that will be 1716. So three different values here, and then 2 is about 300 away, slightly less from the lower quartile. Right, and it's Q1 and Q3 that are going to define what the limits are of our box. And that begins to be a useful kind of limit, and it defines the IQR, or the interquartile range. In our case, that's 1716 minus 1102. That gives us some kind of measure of spread. And note that when we go and we put in our second quartile, we get a little bit of a sense of the symmetry that we might have working or not working. In this case, we have relative symmetry, that the difference between Q3 and Q2 is about the same as Q2 to Q1. It's shifted a little bit closer to Q3, but not a large amount. There's about 300 difference between each of those. Right, so that's the first part of the box. And then we also go and it's almost like going from one standard deviation out, and then we're going to go one more standard deviation out, sort of. We're going to define what's called the whisker. And the whisker is going to be these bounds on upper and lower, at the upper side, it's going to be Q3 plus 1.5 interquartile range as the potential value. I say potential because we're actually going to look at the data that sits within there. Right, so we take 1.5 times this interquartile range. Right, the interquartile range was 614, and 1.5 times that is equal to 921. So Q3 plus 1.5 IQR is 2637. Our max value that we actually have out of the whole whole sample set is 2265. It's quite a bit less than that. So what you do is you actually go, you're going to draw a line that goes up until we reach this Q3 plus 1.5 IQR, unless we reach, or until we reach, that is, the largest data point that's in there, that range. Right? That sounds confusing, I know. So just temporarily put a little dot here at 2637. Now we, with all the data that's plotted, and there in a general sense might be some way out in here, but we go to the one that is within this region, that is the largest one in that region, that's 2265, and that will define our upper limit, or what we call the whisker. And some programs will go ahead and write that number down, 2265, as being up there at that upper level. Any sample points that are outside of the 1.5 quartile range, outside of Q3, those would be outliers. And if we went another 1.5 IQR outside of that and still had data points, we'd call them extreme outliers. Okay, so we don't have any upward or large outliers as defined by this particular process. Down here at the bottom end, we have Q1 minus 1.5 IQR, and that number is going to be 181 for our potential location of our lower whisker. Well, we had 375 is sitting in this region. That was also our minimum of the entire data set. So our cat whisker there just goes down to that one. Again, it's not the overall min in the entire data set. It's just the minimum one that's sitting inside this 1.5 Q1 minus 1.5 IQR. And if you might recall, when we looked at the histogram and we were looking at the stem and leaf plot, I said, well, it sure is tempting to call this an outlier because there's a big gap between 375 and the next one, which was around the 700 region. And I said, well, you know, there's only been 70 samples that we've tested. If we did a lot more, we might find that those spots fill in. And in this particular approach to creating the box plot and defining the outliers, then we find out that now 375 is not considered an outlier. Right, so these are the whiskers top and bottom, and that's your box plot. If you have outliers outside of these 1.5 quartile ranges, then you usually asterisk those or do some other kind of symbol to denote that those are special and different. It all depends on the particular software package that you're using. And as I said, I've done this by hand. There are other packages like Minitab which will do this for you, and they'll do them quite quickly. And my goal here with you is not to develop your ability to create these in a production kind of level, but rather that you understand the bigger scope that these things exist. They do tell you some kind of interesting information that goes beyond what a histogram does and goes beyond what a stem and leaf plot would do. It does give us some idea of the spread if you define the spread as the quartile. If you can also get some sense of the potential symmetry or asymmetry that's at work in the data, and you can also do some identification of outliers or unusual observations. All those are good. If you were to do these for, say, a number of different kinds of processes. Maybe it's different plants that we're looking at. Right? And so here's a figure out of your text that now you got 3 different plants, and here's some measure of quality index, and you can kind of get a sense right away that plant 1 has an average or a median value at any rate that's quite a bit higher than the other 2 plants. And these 2 plants look like they're about the same overall quality, but plant 2 has a lot more variability to it. And so they're useful plots. They're very easy to create when you've got data already entered into a software package, and even if you don't, to create them by hand is really not all that big a deal either.